Okay, before we get to the new stuff today, I just want to touch back on one other thing with these Kirchhoff's loop rule type problems. So we went through some examples on how to do these kinds of problems. One other thing we can do is once you get to the end of this, and you do know what the currents are and which way they actually go. So this is one of the examples that we did. So we solved this one. These currents, these directions. Here's something else you can do with that, is let's say what I want to know is what's the potential difference between any 2 points in that circuit. For example, maybe we're interested in these 2 junctions, and I want to know what's the potential difference between those 2. Well, we had talked about Kirchhoff's loop rule that says if we started someplace and do a closed loop and add up all the potential changes, it better add up to 0. We can actually use, basically it's like part of a loop rule to figure out what is the potential difference between any 2 points if we didn't get all the way back to our starting point. So let's say I want to know what's the potential difference from here to here. So starting at the bottom one, going to the top one. Once we know what the currents are and which way they go, we're free to pick any path between the 2 points we're interested in and add up those potential differences as we're crossing power sources and resistors, and we'll know what the potential difference is between those 2 points. For example, let's take this path first and go this way, around the left-hand side. So I start here, go around like that, end up where I'm interested in, and let's add up all the potential changes around that left-hand side. Well, the only thing I have between my 2 points going that way is one resistor here. I'm going the same way as the current is, and so what is the potential difference that would be, that happens as I cross that one? It's negative because we're going the same way the current goes, and it's that resistor times that current. So if I go this way, I find out that that change in the potential between, it's called A and B, is minus 2 volts. What if I went around the left-hand side instead? Let's start here, go around this way, end up at our point. So I come this way and I go through a resistor. I'm going backwards against the current, so that's a plus. This resistance times that current. Then I go backwards through a battery, so that's minus that, and what do you end up with? What's 12 minus 14? Same thing we had before. Or I can go this way. I can start here and go right up the middle. So I go like this. I go through a battery the normal way, so it's a plus 10 volts. I'm going the same way my current is going. So when I cross that one, I have a minus 12 volts. And so what's our grand total this way? Still minus 2 volts. So we can pick any path we want. Do basically a partial Kirchhoff's loop rule to figure out the potential difference between any 2 points in the circuit. Make sense? Okay. Today's topic is RC circuits, and I did load one more lab on, so it's the last lab that we'll be doing in this section. So for those that are getting a bit ahead, there's an RC circuit lab on D2L for you. And this goes, actually going back to kind of where we started all this stuff when I first had you use these little kits, and you had that big blue thing on there, and you connect it up to a little light bulb, and you flick a switch, and the light bulb will go on and off, and you flick it the other way, go on and off. One way to draw that circuit would be like this, where here's your batteries, here's a switch to where we can either flip it up this way or flip it down that way. If I flip it up this way, then my power source, my resistor, and my capacitor are all in that circuit, and I can charge that capacitor up. When I flick it back down this way, then that takes that battery out of there, and I can discharge my capacitor through that resistor. What we're going to look at today is some more details of what's going on when you're charging and discharging those capacitors. So let's flick the switch up like this so we can charge our capacitor. What we're going to do is start with nothing in our capacitor yet until we flick that switch up here. So I just redrew it here. This would be our circuit once we close that switch. And let's look at some things here. First, let's do this. Let's actually do this to give a start. Let's add up the potential changes around that loop. So let's start here, go around the loop, add up potential changes. So I go through a battery, I go across the resistor. If I'm going clockwise, my current's coming out of that. I'm going this way, so we're going the same way as the current. And then we come across here, and I'm going to, from our QBC that we had before, just solving that for V. And we get a drop across that, and then we're back to our starting point, so all that should add up to 0. So we'll kind of use that as our base to start with. Then let's look at some different times. So when we first close that switch, the way you can say that is at time 0, so right as we're closing that switch. How much charge is on our capacitor?
0.
None. We haven't put anything on there yet. We've got an empty capacitor. So if time equals 0, this part is a 0. And notice what we have left then, if I solve for this, is that or, let me write it this way, my initial current that I'm going to get in this circuit is going to be the voltage across that battery times the resistance of the resistor in this circuit. So nothing happening across here. There's no charge on it yet, which means there's no potential difference across it. I do have a current. Once I close that thing, you saw that because you saw the little light bulb go on. And this is the current I'm going to get right when I flick that switch. Okay? What if instead we look at a really long time? See what that means here in a bit. So we close the switch, let things go for a while. What happens to the current if I wait a long time? Close the switch and wait for a while. What'd your little light bulb do?
No.
Went back out, didn't it? What does that tell you about the current if we wait long enough? There is none. So this part's 0, but now I do have charge stored on my capacitor, or this combination. I do have a potential difference across that capacitor. So solving for that, the maximum charge I can get across that capacitor is the capacitance times that voltage across my battery. So far, not that big a deal. I mean, this says V equals IR. This is our QBC that we've seen before. Where it gets more interesting is what happens between these two times. Between when we first flick this switch and if we wait long enough. So the unfortunate part is this is a nice calculus problem. In fact, it's probably 4th semester calculus. So for any of you who've had differential equations, this is a great differential equations problem. So we'll just jump to the conclusions and see if you recognize what this says and how to interpret this. So if we charge up a capacitor in an RC circuit, here's what happens to the charge across that capacitor. So that charge across the capacitor is equal to what happens to our voltage let me even do it that way. And what happens to the current? So let's see what those mean. See if you're familiar with those kinds of equations. So let's say we're going to make a plot of charge versus time. So charge across our capacitor versus time. At time 0, where should we be on the graph? It should be at 0. So I know we should be there. If I wait long enough, where should we be? At the maximum value, which is this. So at some point, we're going to reach some maximum value. This says how it's going to get from here to here. So what does that look like on the graph? Are you familiar with exponential functions? Give you some choices. Is it that?
That's too easy.
That sure does not look linear. That doesn't look like y equals mx plus b. Does it look like that? It looks more like sines and cosines and stuff like that, so probably not that. So it's one of these two. One or two. Okay. Those are good. So notice it builds up really fast, and then that build up tails off until eventually you reach that maximum.
And does it start at 0?
Yep.
Okay.
Because there's nothing across our capacitor yet when we first put that switch when we're charging up. So notice that the voltage does the same. How about the current? What's happening there? What does that look like? If we wait long enough, how much current are we going to have? We wait a long time.
0.
Yeah, our current shuts off. So if we wait long enough, we're going to end up down here someplace. Where do we start? Right here. So we start up here. And this tells us how we're going to get from that initial current that we have down to 0. Yep. That's a classic decay function. Notice there's something in each of these equations. Switch colors here. That's pretty handy. Is this little thing. And this is something you'll play with in that lab activity. The quantity, R times C, the resistance of our resistor, the capacitance of our capacitor, is called the time constant. That's actually going to control how fast or slow this does to this behavior. In other words, let's look at the voltage one. I know I'm going to start here. I know I'm going to end here. I know it's going to have one of these kind of archy looking things. But is it going to fill like this? Or is it going to fill like this? That's controlled by this time constant. More practically, we can alter either the resistor or the capacitor, typically it's the resistor that they change, to set how long we want to take for that capacitor to fill. So again, you'll play with that and get a little better sense of that. With that, let's take a quick look at discharging. So let's say we've charged things up, we waited a long time, we've got our capacitor filled up, our current's shut off. Then we flick this switch the other way and let our capacitor discharge, so this guy's out of there now. And let's see if we can figure out, without having to do calculus, what happens when an RC circuit discharges. Let's look at these three things. What happens to the charge across our capacitor? I'm sorry, the charge stored on the capacitor, the voltage across it, and the current through our circuit. So again, we're charged up, we flick a switch, we discharge it. If we, well actually, I'm trying to see here. Which one of those graphs over there is this one going to look like, is this one going to look like, is this one going to look like? And once we figure out what the graph should look like, then it's easy to figure out what the equation should look like, because it'll be kind of like those. Watch this part. Where these things with the zeros are whatever it is we started with when we decided to discharge. So whatever our voltage was, whatever the charge was, whatever. We'll see what this means actually. So what's it going to look like? So we're going to discharge. If we wait long enough, where are we going to end up on this graph? Here somewhere. Your little light bulb went off, right? If we wait long enough, what's going to be the potential? Well, look at this one. How much charge is stored on our capacitor? Zero. We dumped everything off of it. And if we wait long enough then, if we've dumped all the charge off our capacitor, how much voltage is across it? Zero. There's nothing on our capacitor. So which one of those graphs does it look like? They're all this way when you discharge. Where this is whatever charge you started with when you decided to discharge. Here's the voltage. And here is your maximum current that you can have right when you first start to discharge that. So again, you'll get a chance to play with that and see that a little bit. I want to show you an interesting, pretty simple but pretty valuable, very practical RC circuit. And so you're going to figure out what this will do. We'll talk about a couple of examples where you can see this. So here's a nice RC circuit. We have a new circuit element in here. So what this thing is it's, one example of what this could be is a light where this is enclosed. Notice I've got a gap in here. And I've got a gas inside here. So maybe it's a bulb or something. I've got a gas inside there. I've got a gap right there. And let's see what this would do when I flick a switch and stand back. So I flick a switch.
This one's standing back.
Oh, this won't be too bad.
Okay.
This is not one where I make you sign a waiver. I got others, things that will do for that. All right, so I flick a switch and start this thing going. So far, Here comes current, goes through a resistor, hits a junction. Can my current go this way? No, because I've got a gap right there. I don't have a way for my current at the moment to get through there. So I start filling up my capacitor. As my capacitor fills, and again, we can control how long that takes with that time constant, with the combination of what this resistor is, what this capacitor is. As that fills, what's happening to the voltage across here? Going up, going down, staying the same, or what's happening? It's going up, right? How is this light in this circuit with the capacitor? What's the arrangement of that light with this capacitor? They're in parallel with each other, right? When circuit elements are in parallel, what's the same across both of them? The voltage. So as I start filling this, I get an increase in the voltage across here, which is increasing the voltage across here. Well, if I'm increasing the voltage across here, what I'm essentially doing inside here is building up an electric field. What's that electric field doing to my little gas molecules in there? If I put molecules in an electric field, what does it start to do to them? That was like when I stuck the balloon on the wall. What's it do to those molecules? So we talked about it when we stuck the balloon on the wall. We talked about it when you go across the floor in your socks and try to touch the doorknob and get zapped.
It's polarizing them.
Yep. You're polarizing the molecules in here. And the larger that potential difference across here, the stronger the electric field in there, the more they're polarizing. Is there a limit to how much I can polarize those things? Yes, there is. Eventually, you can ionize them. You literally start ripping electrons off the atoms. If you ionize that gas in here, you've just made a little pathway right there. Once that ionizes. So if I can get this potential difference to get large enough to ionize the gas in here, now I've got a pathway right there while it's ionized. If I open up a little pathway here, then what happens? At the moment, I've got a whole bunch of excess charge sitting here, right? And it's being forced on there by that battery. Not happy about it, but that's its only choice until I do that, because now what can happen? Got a whole bunch of positive charges sitting here all next to each other. They don't like that. So what can they do once I make a little pathway there? Yep. Let's go like that, and let's forget being packed on here. Let's come around like that. I do that, my little light goes on. So I get charges across here, my light goes on. But wait, what are we doing to our capacitor? We're discharging it, right? What's happening then to my voltage across here if I'm discharging? It's going down, so what's happening to the voltage across here? So it goes down, and eventually it goes down low enough that I'm not ionized anymore. I close that off. So let me stop the story there. What does this do if I close the switch, step back, and watch? It blinks. It'll blink. So once I get a large enough potential difference across here, I get a little path, my charges dump across like that, my light goes on, but I'm losing potential here. Eventually I lose my little path here, my light goes back off. But when it goes back off, I'm building back up here. Goes on, goes off, goes on, goes on, goes off, goes on. And how do I control that blink rate? With that time constant. And by altering that, I can set how I want that thing to blink. Where you've seen this, you know, those basic highway road signs, they're on like little sawhorse things with the big yellow thing like that just blinks. That's how I make those lights blink. Your camera flashes are this, other than it stops it after a single blink. So after a single blink, it pops a switch, and you have to close that switch and charge this up again. So your camera flashes are this, but it's only doing a single blink. Pacemakers are basically this. This is a great way to do anything that you want repetitive and that you want to control that rate. Here's a pretty good one if I can find, yeah. You know, something else that blinks or has blinking behavior that's based on that circuit. Are your windshield wipers. So when you turn them all the way on, it's got a certain blink rate. But most of your wipers these days, you know, you can do an intermittent thing where it blinks at a different rate. What do you physically do to change that? You turn something, right? You want to know what you're actually doing? Especially for those that have used these. In case you haven't used these guys yet, this is a resistor back here. It's a variable resistor. The fancy term for that is it's a rheostat. That just means a variable resistor. And I've got a little dial here where I can turn this and pick how much of this resistor I'm using. When you turn that little thing like this to change that blink rate, that's all you're doing is you're changing something on a rheostat, picking a different resistance, which is changing this time constant, which is going to change the rate at which this circuit blinks. So pretty simple, but pretty handy. And again, with that lab activity, you'll get a better idea of how this time constant works and what a bigger time constant means, what a smaller time constant means. I want to run through one sample problem, and then we'll use the rest of today to get back to lab activities. And then Friday will leave us an open day for lab activities, and next Monday will leave an open day to get everybody caught up on homework problems, lab activities, and things like that. So one sample problem on this stuff, see how this works. And again, when you get to the RC circuit lab, there's some more sample problems there that you can take a look at. Let's say we've got one of these blinking RC circuits, and let's put some numbers on things. Let's say this is 95 volts over here. Let's say the breakdown voltage that I need is 72 volts. That'll ionize this so I can actually open up a little conducting path there. And let's say my capacitor is a 0.15 microfarad capacitor. So what resistor can I put in here that's going to make this blink 2 times a second? So since we're looking at building this up, so filling this until I can get a voltage across here to hit that breakdown voltage over there, we're going to use the charging equations. And you could use either the charge or the voltage one. It may make more sense to do the voltage one. So let's take a look at that, because they're basically the same equation. But since we know voltages, we'll use that one. We don't really know how much charge is going to end up on there yet. We can figure it out, but since we know voltages already, let's use that. So what are we trying to find out of all that? Which one of those things in that equation? R. How are your algebra skills? To turn that into are on one side of the equal sign, everything else on the other. It's not that bad. Let's go step by step. It's not that bad. I need that by itself. Let's bring this over to the other side of the equal sign first. What next? Let's bring the 1 over there. Let's do something just to pretty it up a little bit. Let's get this off of there next. How do I do that? Flip the signs on the other side. Or rewrite this as, in other words, this is plus, this is minus, this is minus. If I make that plus, that turns plus, that turns minus. What next? I need to get that off of there. How do I do that? In words, what you were doing with the other steps, you're doing the inverse operation. What's the inverse operation of e to the something?
Natural log.
Take the natural log of both sides. Now what? Probably do this in just one more step. This is the thing I'm looking for, right? Let's do easy algebra. Oh, sorry. There it is on the bottom there. What happens if I stick it over to the other side of the equal sign? Pops it up to the top, which is where I want it. So that brings this up here. What do I do with all this then? Stick that whole mess to the other side of the equal sign. If it was on the top here, ends up on the bottom down there. Then all we have to do is plug numbers in. So the capacitance, that's easy. That's 0.15. Oops, let me change this, sorry. Let's make that, I'm so used to writing micro. Let's make this full farads, so not micro. Sorry about that. So natural log of 1 minus. Which v is which? So what are these two v's?
So is it your initial one when you start with?
Yep. That's what our voltage is across the capacitor at any time relative to our maximum possible, which would have been our battery. This is the one we want to match that guy. So we're going to run that voltage across the capacitor up to the 72 volts. So that's this one over this one. So one more number, and we're home free. How come I'm not going to put a 2 on here?
Twice per second.
Yeah, what does blink twice per second mean for a time that we're going to stick in there? It blinks once every half a second. So here's every blink will happen every half of a second. And plug all that in, do that on the calculator, and try this just to make sure you know how to use your calculator right. That says if we put a 2.35 ohm resistor in there, this will blink 2 times a second. If I want to blink at a different rate, I can put a different resistor in there. And I can put resistors in, figure out what's my blink rate now. It's all good. Any questions there? Okay, so that should get you set up for all the rest of the lab stuff. And